Good afternoon and welcome to the Sustainable Materials Management webinar series, a joint effort between the National Recycling Coalition and the Pennsylvania Recycling Market Center. My name is Wayne Bowen and I'm the Program Manager for the Recycling Market Center, and I will serve as your moderator today. We would like to extend a special thanks to Bob Hollis of the Mobius Network for providing the webinar management software for this series, and Lisa Ruggiero of the National Recycling Coalition for providing technical support. Today's webinar focus is on the use of Digestate from anaerobic digestion facilities as a compost. Following the presentation, we will conduct a question and answer session. If you do have a question or comment, please use the GoToWebinar dialog box located in the control panel on your screen. You may also use the dialog box to request assistance if you are experiencing technical difficulties during the webinar. And now I'd like to introduce our presenter, Amber Blythe. Ms. Blythe is an application engineer at Biofirm Energy Systems. She has a Bachelor of Science degree in chemical engineering from the University of Wisconsin-Madison. During her studies, she focused on renewable energy and interned at GE Transportation as a test engineer, as well as Sanomatic Inc. as new product development engineer. Her focus at Biofirm is on business development. And now I'd like to hand the program over to Amber.
Thank you, Wayne. I'd also like to thank everyone for joining today, and I hope I can inform you a little bit on how anaerobic digestion and composting can be incorporated and work well together. A little bit of background on Biofirm Energy Systems and who we are. We're a subsidiary of the Viessmann Group. The Viessmann Group was founded in 1917. It currently has over 9,600 employees, and it does $2.4 billion in revenue each year, with 60% of their business being in the renewable energy sector. This is a range of their products, ranging from heat boilers to anaerobic digestion. Biofirm Energy System is located in Madison, Wisconsin. We've been here since 2007. And we're a technology supplier of anaerobic digestion for almost any type of feedstock. We supply both dry and wet fermentation technology in North America. This is a range of the technologies we offer. The first diagram you see at the top is dry fermentation, which this will be focused on. So dry fermentation feedstocks typically are yard waste, food waste, any sort of structure material that can be stackable. This type of system is a garage system, batch system. You'll load it up, close the doors, remove oxygen for 28 days, and let it ferment to produce biogas. Biogas is collected and then fed to either a CHP or another form of equipment which utilizes it to make electricity and heat. The second system is a wet fermentation. This is what most people are familiar with. It's what you'll see on the large dairies, large farms across the U.S. This system is a large, complete mixed tank system. You pump your feedstock into the digester. A retention time is typically 28 days. Again, you allow it to produce gas. You collect the gas and you burn it. Typical feedstocks for this type of digester are liquid manure, corn silage, food waste, any sort of energy crop. The last technology is our newest model. It's a small containerized digester. It's slightly larger than a shipping container and it's all in one. So this digester, it has the digester tank and CHP, the energy production unit, all in one container. This unit takes feedstocks such as food waste, manure, energy crops, a wide variety. Here's a breakdown of the three systems again. So the wet digester, which is people are most familiar with, is what's called a wet system. It takes feedstocks that have a range of 8 to 12% total solids in it. The feedstock needs to be pumpable. That's one of the key factors. The second system is our OICO, our plug flow, which is similar to that smaller containerized unit, and it takes feedstocks from 10 to 25%. And the last one is the dry system, typically a feedstock range of 22% total solids and higher. Next slide. Again, we'll focus on this system, the dry system. So this is a diagram of the dry system. One is the biomass storage area. So typically, plants will have deliveries every day, so you need an area of where to store that material while you're not loading the digester. So that's what this area is for. Number two is the mixing area. The way this works is you mix half fresh material and half digested material and then reload it into the digester. This is done to inoculate the material to help heat up the new digestion process, to help the bugs be present in the new process, and to make your biogas production quicker. So once it's mixed, it's loaded into 3, which is the fermentation chamber. This chamber looks similar to a garage. They're 99 feet long, 23 feet wide, and 11 feet tall. You load the digester about 80% full and then close the doors. The bugs present begin to break down the material and produce biogas. Biogas is a mixture of 55% methane and 45% carbon dioxide. There are a couple trace materials in there, such as hydrogen sulfide, ammonia, water vapor. So as the gas is being produced, pressure builds up in the chamber. And once your pressure reaches a certain point, gas moves from the chamber to number 4, the biogas storage bag. It's contained in this bag. It's collected and allowed to mix, and then you feed it from the biogas storage bag to your energy production unit, whether that be a CHP, which is a combined heat and power unit, a boiler, or getting more popular is CNG, where you clean the gas so that it's only methane, and then you compress it for vehicle fuel. One thing to mention is that these garages, these fermenter chambers, are kept sealed for 28 days. So each one of these units is loaded at different times. So once a week, you'll switch out a fermentation chamber so that each chamber is at a different production time, where chamber 1 might be starting up producing biogas, chamber 2 is well into the process, and the gas produced at that stage is much richer. The reason you do this is so that you don't have a large fluctuation in the content of the gas, so that you're not going from 12% methane to 55% methane to 70%. The biogas bag allows all those gas mixtures combined and make an even 55% methane. Again, here's an illustration of how the process works. The box you see is an example of a fermentation chamber. You load it up with your substrate, your feedstocks, up to about 80%. During that 28 days, we spray a liquid material onto the pile. This is done to help speed up the digestion. The liquid material is called percolate. It's a high microbial liquid so that the bugs are able to move through the piles, the substrate piles, much easier. That liquid material then moves through the pile to the bottom, where it is drained out and collected into what is called a percolate storage tank. This is just a storage area for the extra liquid material, which also acts as a wet fermentation chamber. Both the liquid storage tank and the fermentation chambers produce biogas, which moves from the chambers to the biogas storage and then to your CHP. This whole operation is kept under a biofilter so that if any part of the process, your substrate handling, your feedstock handling, mixing, opening of the chamber's doors is happening, that all the gas that's produced in that area is collected and goes through a filter so that no odors are released to the surrounding area. So this is kind of just a summary of what I previously talked about. The digestion process is 28 days. This can range from 20 days to 40 days depending on what your feedstock is. Food waste tends to break down much quicker than substrates that are more coarse, such as animal bedding and yard waste. Minimal liquid is needed to be added. As digestion happens, water is produced, so you collect that water and you store it in the liquid percolate tank, which is then used to accelerate the digestion process. Materials are stationary, there's no moving parts in dry fermentation. The input material is reduced by 40% as energy is extracted. The end product, which you remove from the digester, is called digestate, and this is where composting is involved. So I kind of wanted to go over some myths, common myths of anaerobic digestion. Myth number one, it's smelly. A lot of people think of digesters and they think that, you know, they're odorous and they smell worse than dairy farms. But this is not always true. This is why our whole operation is kept under a biofilter. So any odors that are emitted during the process, they're collected and moved through a biofilter. Our biofilter that we use at our facility here in the U.S. is a biological biofilter. The gas will move through a biological filter where the microbials eat the smelly components and release clean air. The smelliness of the digester depends on what substrates you're handling. Some substrates break down much quicker, reducing more odors, and other substrates don't. Next slide. Another common myth is that all the valuable nutrients are lost during the digestion process. This is not necessarily true. During anaerobic digestion, the volatile organic compounds are converted to biogas. Biogas is a combination of methane and carbon dioxide primarily. Methane is made up of carbon and hydrogen. So the main components you are losing from your substrates are going to be carbon and hydrogen. After the digestion process, typically the digestate is composted further. So in order to get your carbon to nitrogen ratio back up, you'll have to add a carbon substance, whether that be bulk wooding, wood material, yard waste, or whatnot. During anaerobic digestion process, any nitrogen, phosphorus, or potassium in manure or food waste is converted more easily to absorbent nutrients. These absorbent nutrients are actually better, meaning that they're higher quality nutrients. And also, one thing to mention is that the volatile organic compounds, which are the smelliest compounds in your feedstock, are converted during anaerobic digestion, which reduces the odor issues. Next slide. There's a lot of talk that anaerobic digesters just don't work. One thing to mention is this is a natural process. It occurs every day in nature. It's been occurring for the past 2,000 years, and we've been harnessing this application for over 200 years now. It was first introduced at wastewater treatment facilities, and once they realized the benefit of the gas that it produces, it was utilized on farms and other applications. In the 1800s, they would use the sewage gas from the sewage drains to power the street lights. In 2010, it was reported that the U.S. had over 162 anaerobic digesters, generating over 453 million kilowatts of energy in the U.S. from agriculture operations, typically farm-based digesters. This is enough to power over 225,000 average size homes. And as most people are familiar with, Germany is the leader in anaerobic digesters, having over 6,800 large-scale digesters ranging from farm-based to food waste applications and whatnot. So our first installation of dry fermentation in the U.S. was in Oshkosh, Wisconsin. We had a partnership with the University of Wisconsin-Oshkosh. They have a goal to be off-grid, be carbon neutral by 2025, and this was one of their projects to help them meet that goal. Their facility is a 4-fermenter dry fermentation facility. Their installed electrical capacity is over 370 kilowatts. Their feedstock consists of food waste and yard waste. Food waste primarily from grocery stores, and the yard waste from the campus and the city of Oshkosh itself. As I mentioned, it's a 4-fermenter vessel. These are actually short fermenters. The typical fermenter is 99 feet long. They went with a shorter one because they had concerns with not getting enough feedstock. So they are 65 by 23 by 13. Construction began in September 2010, and they've been over a year and a half in operation now, producing gas. As I mentioned, their feedstocks consist of food waste from the local grocery stores and restaurants, yard waste, which means grass clippings, leaves, shrubs, and wood chippings from both the city of Oshkosh and the university landscape itself. Post-consumer food waste, they're taking in a small bit of post-consumer food waste from the university's cafeteria, and animal bedding from the local farms. So a quick flow chart of how their process works. They take in the food waste, which is the bottom slide, the bottom picture you see, the green one. As I mentioned, it's mixed with pre-digested material. It's then loaded into the digester chamber with a front-end loader. Out of the digester after 28 days comes the Digestate, which looks similar to the third picture you see with the front-end loader. Digestate looks similar to wet compost, very earthy. As it breaks down, it produces biogas. In their application, they burn the biogas to produce electricity and heat. They produce enough electricity currently to power 10% of their school's need. So they have created a partnership with a local composter. The composter takes the Digestate and composts it further to a finished product. The Digestate that comes out is typically about 28% total solids. It looks like I said, wet compost. The volatile solids is typically in a 48% range of the total solids, and the pH ranges from 7.8 to 8.6. The composter then uses a windrow to aerate and further process this material. There's minimal addition of carbon used and minimal monitoring. He monitors temperature and pH. It's a very low budget operation, but it seems to be working well for him. So some of the negatives and positives. The positive is that the NPK ratio is retained through this process. Basically, all you're removing is the carbon source to produce the methane gas. The Digestate that comes out of a digester is a very uniform, homogeneous material. Contaminants are easily processed. The negatives is it can require additional carbon source depending on how much was abstracted during this process, and it can have a high moisture content. Conclusions and further research. Enhanced aeration may reduce the time required for composting of this type of material. faster turnaround time, and a more complete breakdown. Carbon addition. We need to determine how much carbon is actually required to get your NPK or NCN ratio. And lower moisture content, some sort of separation may be required to add more benefit to the composting process. I think that's all of it. So
Okay.
I'll open it up to questions.
Yes, thank you, Amber. And we're now going to field some questions to Amber. And we also have Stephen Sell from BioFirm with Amber to help with answering questions. Again, if you have a question, please enter them on the GoToWebinar dialog box. And the first question, and this is usually the first question, is this presentation being recorded? And the answer is yes. After we do some editing, the presentation will be made available on the National Recycling Coalition and the Pennsylvania Recycling Market Center websites. So I'll go to the first question. What is the biofilter made of, and what do you do with the material when it is spent?
I can answer that. So our biofilter is a couple layers. The first layer is going to be water. The second layer is going to be lava rocks. And on top of lava rocks are used to create surface area for microbes to grow on. In other applications, you can use a woody waste instead of a lava rock, depending on where you're located and how expensive it can be. And so the air, the gas, is bubbled through the water and then moves through the lava rock where the microbials eat it or consume it and remove those contaminants.
And as far as the duration and the length of how long that material will last, there has been a lot of research performed in that material at the University of Wisconsin-Oshkosh, and they've never really swapped out that material during the last 5 to 10 years for other small projects. So we are still kind of looking at what the lifespan would be of the material.
Okay, the next question is it's actually a comment concerning the high moisture content of the digestate, and the commenter basically stated that it seems like the material should be composted on a liner or a pad, and I guess that would depend on the local regulatory requirements. But Amber and Stephen, do you want to comment on that?
It's definitely possible to remove more moisture from the digestate. This composter is not. So when he comes to pick up the material, it's been sitting on our concrete inside of our mixing lobby for a few days at that point. So any free water is drained out of it for the most part by the time he would take it and pick it up. I'm not sure how much dry material he mixes it with, but I know he does not look at the carbon to nitrogen ratio too much prior to doing his piles with digestate, just because they wanted to see what the raw digestate would do by itself.
And a related question is what is done with the final compost?
It's sold in bulk to local municipalities and households.
Okay. This question is concerning biodegradable plastics. Can this type of facility compost those materials, the ASTM compostable materials?
The university has done a lot of research on that with the state energy office. Some of those materials, depending on what they're made out of, have broken down in the digester, but a lot of the compostable plastics require certain temperatures, a temperature of 180 to break down. And we run our digester at mesophilic temperatures, which means a temperature of approximately 104. So when you do put those plastics in the digester, you see a little bit of melting, degrading, but it doesn't degrade as much as it will in the composting afterwards.
Okay, another related question. How big of a problem is packaging contamination, and how do you manage it?
It depends. In Germany, what they typically do is they'll run it through a hammer mill beforehand. So the hammer mill will remove the plastics, the metals, any other contaminants that might be present. The feedstock that's going to the university is very clean. There's very little packaging present, so they don't see it as big of an issue. The food waste from the grocery stores, they tend to depackage beforehand.
An additional note to that is the packaging doesn't harm our process at all. It can go into the digester. It's just not going to produce energy. So by putting in contaminated materials, it's just going to have to be separated at some other point during the process. So usually at the back end during your composting is where you would remove it at that point.
You mentioned pre-digestion of the material. Where does that occur in the facility?
There's no pre-digestion. Could you ask them to elaborate a little?
Well, basically, where is it stored prior to placement into the chambers?
So if you want to flip back through slides. So at our Oshkosh facility, all this area you see, Area 1, Area 2, Area 3, 4, is all enclosed in one building. It's all contained, and that's done to contain the odors primarily. So Area 1 is going to be where they deliver the feedstocks to. So when a truck comes in, he comes in on the left side. He'll pull in and dump his material in there, whether that's food waste or yard waste, and then he'll pull out the right side. So it's a through building. There's a garage door on both the left side and the right side of the building. And so all that material is stored in that Area 1 until a digester is opened and ready to be reloaded. And so then we pull some material from Area 1 and mix it with old material in the Area 2 right in front of the fermenter itself, and then we load it in.
Next question is, what is the typical NPK analysis for food residual digestate?
I don't think we actually have those numbers available on any of the current feedstocks we've been using, and most of our feedstocks going into the digester, the food waste component's only 10 to 20%, so it's not entirely food waste going in there. That's definitely something we want to look into a little bit more, and I know the university is planning on doing some research with that and this year in line with the other compost research that they want to do as well.
Is there any testing done on the digestate for metals and pathogens?
They have looked into it, I know, because they're trying to get the clarification between Class A and Class B biosolids. They don't do it on a consistent basis, but they have done it on a few batches, and I don't think I have those available offhand. I'd have to go to the university to get the data.
This question is concerning the sizing of the materials. Does the yard waste need to be chipped or size reduced before being put into the chamber?
No, not necessarily. You want these materials to be stackable, and if you're putting too small pieces in there, then it's not going to be stackable. So typically, we'll just load them in as is.
This question asks, is there an ideal feedstock? What type of material gives you the best bang for the buck?
For this type of system, I would say as much food waste as you can possibly put in there, but yet you do need that yard waste for that bulking agent. So what we typically do is about 60% yard waste or any kind of agricultural waste and 40% food waste. Food waste breaks down very quickly and it's a good biogas producer. So whereas yard waste takes longer to break down, as you know, in composting as well. And so it's not as great of a biogas producer.
Mm-hmm. This question deals with cost per ton after processing. Any tip fees involved?
Right now, the university just has partnerships. This facility itself just has partnerships with haulers they don't have to pay to have it hauled, therefore the hauler doesn't have to pay a tipping fee. But in typical operations, we would ask for a tipping fee that's slightly lower than what the landfill is asking for. So in Wisconsin, it's very low. It's about $35 per ton to go to the landfill, whereas on the East Coast, it can be anywhere from $60 to $100 per ton. So in that case, we'd ask for, 60 to 80% of that tipping fee, just so a customer would rather bring their waste to us than to a landfill.
Okay. Related question, the cost of the facility itself, has there been a number put on that? And have there been any studies on return on investment for the facility?
Yep, that's part of what I do. And so it's all incident specific depending on where you are. As I mentioned, tipping fees, electric costs also, depending on where you are on the East Coast and the West Coast, electricity prices are much higher, so you can get more revenue from the electric production, whereas in the Midwest they're not. This facility itself cost about $3.6 million. I don't remember off the top of my head what their ROI is, but if someone would like to email that question to me, I can send them back a flyer with all that information.
Okay, next question. If composting were not an available option on site, what would be the most valuable alternative for the disposal of the digestate, and could it generate any side revenue?
So it's a valuable fertilizer, and it can be sold as is as a fertilizer, or it can also be separated into a liquid and a solid stream. The solid stream being more used or more likely to be sold in the city for, say, flower beds or household use, but it can also be sold in bulk to farmers as well, because they can be trucked further and the hauling cost is less since there's less moisture in there. The liquid portion is it's wanted by most farmers because it does contain that high nitrogen component from just the solubilization of the nitrogen, and that's typically what we've done with some of our excess liquid at this site. Is it's been given to or sold to farmers, or like Amber said, there's an agreement between the farmer party bringing in bedding material and exchanging it for some liquid fertilizer.
This one, you're going to have to pull out your crystal ball. What is the outlook for AD facilities using municipal solid waste derived feedstock? And how many facilities are operating and how many are planned?
All right, we get this a lot actually. I've seen a lot of RFPs recently that are asking for municipal solid waste. In Europe 10 years ago, what happened was no one was allowed to landfill anything anymore, so gasification became very popular. Food waste was separated out and sent to digesters, and plastic was typically burned in pyrolysis or recycled. And so I think that the same thing is going to be happening here in the U.S. In Germany, they have 2 facilities that are taking not municipal solid waste, but separated organics out of municipal solid waste. And in the U.S., I think it's going to become more and more popular. The nice thing about this style digester is that contaminants aren't going to upset the digester. There's no moving parts, there's no pumps, there's no mixers that any contaminant could get tangled around or caught in and put a halt to your operation. I believe that New York City right now is investigating the use of a digester for their municipal solid waste. What can't be digested will then be landfilled, and what can be digested will be further processed to an end product, a sellable product. So I think it's becoming more and more popular. I don't know what the outlook is per se.
What is the average cubic foot of methane produced per ton of feedstock?
Cubic feet per ton. Hi, this is Doug. I'm also a biologist who works with Steve and Amber. You could expect the We expect between 1,800 and 3,000 cubic feet of biogas at roughly 55% methane per ton of food and yard waste mixed.
So it depends on what your feedstock is. If you're putting richer feedstocks in there, such as food waste, you're going to have a higher gas production. Whereas if you're putting more structural material, such as branches and dry leaves, you're going to have less gas production.
The food waste component of that alone could produce over 4,000 cubic feet of biogas, so that would translate to about 2,500 cubic feet of methane per wet ton.
Next question is, what is the processing capacity per year for the Wisconsin facility?
They're taking in about 8,000 tons per year currently. They could probably increase that slightly larger, but again, this is the shorter. They put in a shorter unit. Typically, we'd look for 10 to 15,000 tons per year as a processing facility.
Okay. I think that's all the questions. That was a great presentation and great questions from the audience and great answers. So we're going to close this webinar out today. And again, this webinar is being recorded and will be made available on the NRC and RMC websites. Again, thank you for joining us, and we hope that you join us for next month's webinar, scheduled for Tuesday, March 19th at 1:30 p.m. And thank you, Amber and Stephen.
Thank you.
And Doug. And have a good day.